Welcome back, physics fans. Today we have Professor James Berry from Iowa State University. James Berry did his PhD at Yale. He was a postdoc at MIT under distinguished professor faculty. Went to Brookhaven National Lab as a research scientist, and then went to his job in Iowa State in 1975. He's an expert on quantum chromodynamics and nuclear physics in general. And today I'll talk about quantum Hamiltonian physics with supercomputers.
Thank you very much, John. Great pleasure to be back in Lawrence. Thank you. I'm going to take a little bit of a different twist on the science and mainly try to motivate you to be interested in what's going on in the world of high technology with new tools for research, especially supercomputers. And just to set the stage, this is a plot updated every 6 months, which shows the computing power in terms of flops per second, floating point operations per second, teraflops, petaflops, up to exaflops. An exaflop is 10 to the 18th floating point operations per second. Today's supercomputers have moved steadily upwards to the point of peaking out currently at 30 petaflops per second. That's the Tianhe 2 supercomputer in China, #1 in the world. #2 in the world is at Oak Ridge National Lab. That's Titan at about 20 petaflops. And along with that, you have the sum of the top 500 supercomputers, what they can give you as an aggregate amount these days. And the lowest on the ladder of the 500 is down here. So the basic idea here is semi-log plot, nearly linear trajectory. And this means that the power delivered to the hands of the scientists has been on a very steadily increasing, roughly doubling every couple of years, performance. And this motivates us to think really hard about the science we do and the science we want to do. What kind of problems can we solve today that we could not solve 2 years, 5 years, 10 years ago? And what kind of forefront issues and questions can we ask? So that's the background. And I'll come back at the end to talk a little about the industry's interest in this set of developments. Now science, physics in particular, but chemistry also and other areas of science have long been interested in what kind of tools we can use to solve the problems that interest us. And very often these tools, not just in computational physics, but also in experimental physics, result in Nobel Prizes. And this is just to make you aware that there have been prizes awarded in the area of what we might broadly call computational physics. And it leads to lots of interesting results that gain headlines. For example, simulations of supernova collapse are now reaching the degree of realism that allow us to understand the multi-scale, multi-physics that's going on during that fraction of a second or so in which a supernova collapses. And this is pretty exciting because that's a pretty dramatic event and is associated with generation of new elements and lots of mysteries about what's going on with neutrinos and other interesting aspects of supernova collisions. Now I want to dive a little bit deeper, and I'm going to talk first about non-relativistic applications and then a little bit later about relativistic applications of the specific kind of problem that I've advertised, which is Hamiltonian quantum physics. Now we all know from our elementary quantum mechanics text what a Hamiltonian is. It's the operator that has a kinetic energy and a potential energy, and we're trying to solve for, among other things, say the bound states or the scattering states of our quantum system. Well, if you upgrade that to the many particle problem and put in on top of that, we're talking about strong interactions, the nuclear strong interaction in particular between neutrons and protons, and also the Coulomb interaction between the protons themselves, you have a very complicated problem to solve, even if you're just trying to solve the Schrödinger equation, say, for 12 particles. Let's say carbon 12, 6 neutrons, 6 protons. This is a computationally hard problem. There are a number of techniques that have been developed over the last few years, all of which are using supercomputers to try to solve them, especially these larger supercomputers. And I'll tell you about one set of techniques, not because they're maybe providing the latest, hottest results, but they have more general applicability, as I'll later describe for the relativistic problem. Some of the questions that this particular set of techniques is capable of addressing are listed here. These are the physics drivers for what we call conventional nuclear physics these days. And it includes, in our map of problems we try to solve, how do we actually use quantum chromodynamics, the theory of the strong interactions itself, to solve for the properties of nuclei. So these are some of the big questions. This on the bottom here, I just wanted to point out Titan at Oak Ridge National Lab is number 2 on the top 500. Mira at Argonne National Lab, number 5 of the top 500 computers in the world today in terms of numbers of floating point operations per second. Some of the calculations I'll show have been done on actually all 3 of these computers. So the basic problem is simply stated, and again, this is elementary quantum mechanics, but upgraded to the nuclear strong interaction problem and also to the many particle problem. If you like, the Schrödinger equation for up to, say, 12 particles is just a coupled set of differential equations involving the degrees of freedom, the coordinates of all those 12 particles. We can take that problem and write it as a Hamiltonian eigenvalue problem, where the Hamiltonian is acting on its eigenvector, which is itself a function of all the coordinates of all the particles in the problem, gives you your eigenvalue times that wave function back again. That's the standard eigenvalue problem. For the nuclear problem, that Hamiltonian is a sum of a kinetic energy part. This is the relative motion kinetic energy operator of all the pairs of nucleons, neutrons and protons in the system, your 2 nucleon interaction, the strong nucleon-nucleon force, and these days we have theoretical derivations of 3 nucleon forces, those that cannot be decomposed into a succession of 2 particle forces. And actually the theory based on QCD even gives you more complicated interactions as this. Fortunately, there's a hierarchy that this dominates the physics results. These end up being smaller, sometimes non-perturbative corrections, but still smaller, subdominant to these. And so we expect that hierarchy to continue. And therefore, most of the results to first approximation should be given by these first 2 terms. And that's going to be the dominant set of results I'll show you today. Now, the eigenvectors that you get, of course, they give you the so-called density matrix or probability density for the nucleus, and the wave functions that you get will give you access to any experimental observable in principle. This could be quadrupole moments, this could be transition rates, it could be scattering cross-sections. So in principle, we have access to all other observables, not just the eigenvalues, the binding energies, if you like, but also to scattering observables. So if we can solve this problem with high precision, we have a chance of addressing some of those questions I mentioned on the previous slide. Now, how do we go about that? The technique we are going to talk about here, and for all the results, the non-relativistic and the relativistic results, involve a suitable choice of what we call an expansion basis. Each eigenfunction will be represented as a superposition of what we call basis states or configurations. If you're a quantum chemist, this is called a configuration interaction method. So we're going to take as our configurations Slater determinants of single particle states for each of the A particles in the system. And each of these single particle states is a function of the coordinates of all nucleons. So that determinant, multiplying it all out, takes care of the Pauli principle, the anti-symmetrization between any arbitrary pair under the exchange of that pair. That's the reason for picking a Slater determinant. If we're doing a boson problem, that would be a permanent. That takes care of the symmetry between the bosons. So aside from whether it's a determinant or a permanent, the bottom line is that we're using these single particle wave functions to build a set of basis states in which we're going to solve for these coefficients to give us the total wave function. And all particles of the systems we'll describe are going to participate on an equal footing. So let me go to the next slide to talk a little bit about the choice of single particle states. For many reasons, it's convenient analytically and numerically to pick a harmonic oscillator, the standard three-dimensional harmonic oscillator, as the generator of these single particle wave functions. That's a textbook problem. You know the solutions of the three-dimensional harmonic oscillator. They're analytic functions. Then we'll build multi-particle states out of determinants of those single particle wave functions. Now, in principle, that gives us an infinite basis. There's an infinite number of such Slater determinants. So we have to introduce some sort of regularization in this scheme. And then we have to study the results as a function of that regularization scheme. How does that work? Well, I take the case of lithium-6. Lithium-6 is 3 neutrons, 3 protons. And we're going to pick configurations where the 3 neutrons and the 3 protons are each allowed to go through excitations of this harmonic oscillator basis up to some total number of oscillator quanta. Remember, an oscillator quanta is you move one particle up one shell of the harmonic oscillator. That's 1 unit of the quanta. So if I say Nmax, which is the cutoff parameter, 6, that means I'm keeping all possible arrangements of those 6 particles sharing 6 excitation quanta. So they start from 0, go up through 1, 2, 3, 4, 5, 6. That's a simple case where we build all the configurations up to this particular cutoff. That's called a many-body regulator, and we have to study our results as a function of that particular cutoff. Is there any question about this regulator? This is key to what's coming next. So, okay, let's go ahead. So how does the size of the calculation we're trying to do depend on that one regulator? Well, that will depend on the nucleus itself. And then this will also dictate what kind of computer we need to solve the problem. So it's perhaps a little hard to see. This is oxygen isotopes from oxygen 12 up to oxygen 28. And what's plotted here is the function of that cutoff parameter up through about 14, the size of the matrix that we're talking about. It starts at 1, it goes up to 1 billion here, 10, 100, 1 trillion here, and on up. So the matrix dimension is growing basically exponentially with that cutoff. Now, that's just kind of information. What's the value of this information? For the strong interactions that we're dealing with, we typically want to have that cutoff at least up to 8 or 10 before we can see the trend of our results to be able to extrapolate to the infinite matrix limit. The infinite matrix limit is the exact result we're trying to get to. But fortunately, the results are sufficiently well converged by the time we get up to here that we can make a simple extrapolation and get the exact answer with some uncertainty. Now, up here on this side of the graph, I indicate what we can do with a petascale size computer. That's what current supercomputers. So we can be in the range up here for supercomputers that are currently available. This leaves out the upper end of our oxygen isotopes. These days, we can probably get up to about oxygen 24, maybe 22 or 24. We can treat a 22 particle problem with enough precision to get the exact spectroscopy and wave functions within extrapolation uncertainties. At the exascale, which is the reason for putting this on there, is in the last few weeks it's been announced that the United States is going to build an exascale computer. Exascale, 10 to the 18th floating point operations per second. That's 50 times bigger than the biggest computer today in the United States. 50 times. And this brings in all sorts of questions about power consumption. Do you have to build a separate power plant for it? Because it'll take hundreds of megawatts to run such a computer, not to mention the building size and all the rest. But if we get to exascale, basically all the oxygen isotopes and many other nuclei will be accessible to us. Now the rest of this is just looking at other nuclei. The rapid growth is always exponential, and there are other ways of measuring the computational complexity that I'll just leave for private discussions. At the end of the day, you pick your Hamiltonian, you pick your nucleon-nucleon interaction. This will be an interaction that's a strong force. It describes extremely well all the two-particle scattering data, the nucleon-nucleon cross-sections and deuteron properties. And then you say, solve that lithium-6 problem. And you solve it as a function of that cutoff parameter, n max. And the results you get are the spectra. Here's the lowest, say, 6 states of lithium-6 with that interaction as a function of the cutoff. And when I say extrapolate, I mean the trends are so smooth that you can, at some point, begin to extrapolate from the lower spaces up to the current space. And this is the sequence of extrapolants indicated by the dotted lines. So already at about n max 8, we're getting a very good indication of the converged eigenvalues, wave functions, and other properties. And the uncertainties are indicated by these vertical bars. So this is just a kind of a background problem to tell you that we can indeed solve the 6 quantum particle problem exactly enough to get high precision results for that Hamiltonian, and then we can go and compare with experiment. And that's not perfect agreement, of course. There seems to be an overall shift of a few hundred kilovolts here, which is either a defect of the interaction itself or an indicator that we really do need those free particle forces, those subdominant contributions that I mentioned earlier. They've not yet been brought into this calculation. So you see a whole lot of the story that we're talking about with supercomputers right here. Can you go high enough that you can estimate the result of an infinite matrix limit and get the uncertainties so that you have meaningful comparison between theory and experiment so that you can draw strong or firm conclusions about the adequacy of the underlying theory, the Hamiltonian in this case. Other things can be derived. For example, this is a case where you look at the one-particle density distribution at the end of the calculation. Beryllium-9 has 5 neutrons and 4 protons. And we can take a look at its one-particle density distribution, and we see various peaks in the density. This is further analyzed to show that these are 2 alpha particles, 2 helium-4 nuclei, and the cloud is coming from the neutron. And we can subtract the neutrons, subtract the protons from the neutrons and see the cloud itself, and that's basically forming a torus on which the 2 helium-4 nuclei are sitting on either side of that torus. So think of a donut with 1 helium-4 on one side and 1 on the other side. So this is what the microscopic theory solving the 9-particle problem allows you access to see. And this has various experimental consequences. Okay, so that is a background on the non-relativistic problem. Now I know that locally here at KU there's a lot of interest in quark systems, multi-quark systems, quark and gluon systems. So I've selected another subject which is also being addressed with supercomputers. Again, a Hamiltonian problem. And the reason this becomes a Hamiltonian problem is because you take your quantum field theory as your starting point, relativistic, fully relativistic quantum field theory, and instead of going through your textbook perturbation theory treatment, we go a different way. We take that and convert the Lagrangian of the theory into a Hamiltonian. You know that you have that pathway open to you. You can derive a Hamiltonian framework from a Lagrangian framework. And it's most convenient to do that for technical reasons in what's called a scheme introduced by Dirac called the Lightfront Scheme, where, and now I'll start by reminding you what your usual non-relativistic Hamiltonian problem is. Imagine that all of space is on this plane. It's a 2D space, and time is a vertical axis. In usual quantum mechanics language, in your textbook Hamiltonian treatment, the Hamiltonian is defined to evolve the quantum state of your system from one fixed initial time, indicated by this plane, to all future times. Okay, it could also evolve it backwards in time, right? I mean, that's the Hamiltonian for you. It generates the time translations for you. That's quantum mechanics in the usual textbook sense. So that's the time-dependent Schrödinger equation. Now update that to the time-dependent many-particle Schrödinger equation. Same thing. If you have your Hamiltonian and you start the system off at some time t0, you can evolve it for any future time. Dirac said that's not the only way you can do quantum mechanics. So if you look back in 1949, Dirac posed two other ways to do Hamiltonian quantum mechanics. This is one of them. This is more convenient for relativistic problems that we deal with. So instead of having the system evolve from, say, a fixed point in time, you have the system evolve from another surface which is tangent to the light cone, and future evolution is along this direction called light cone time. You can convince yourself that you sweep out all future histories this way, you sweep out all future histories this way, no matter where you start the problem. That's called Hamiltonian light-front quantized field theory. It's a specialty area that's been getting more and more attention because this particular approach has a lot of similarity with the non-relativistic problem I just described earlier. Among other things, it opens the door for us to use our Hamiltonian techniques that I just described for the non-relativistic problem for a fully relativistic problem. The challenge is to derive, first of all, what is this Hamiltonian? And there we can take QCD or QED, quantum electrodynamics, as your starting point, and derive it. And it's actually deceptively simple. When I derive that Hamiltonian, and now there's also the tricky part of fixing your gauge, and the most convenient gauge choice for those who are technically inclined is called the light cone gauge. Once I fix that gauge, what I have is only three possible processes for the coupling of a fermion to the gauge field. And in QED, that's a photon. In QCD, that's a gluon. Initially, that's where you radiate or absorb your vector field on your fermion. You can exchange in what's called an instantaneous exchange graph. This arises from the gauge fixing. And another graph where you have the fermion instantaneously emits and absorbs the vector boson. This is higher order in the coupling, as is this. But these are consequences of the gauge fixing. At this level, quantum electrodynamics and quantum chromodynamics have the same processes, and there's only three of them. So it's deceptively simple. Quantum chromodynamics brings in additional vertices. Your Hamiltonian will couple your gauge fields to itself. It's so-called triple gluon coupling, quartic gluon coupling, and you pick up another couple of so-called instantaneous graphs. The bottom line is, I can imagine that my Hamiltonian problem framed in this way is just a matter of figuring out how to write down a basis representation for any system of interest. Let's say it's a meson. So I'm going to start with a quark-antiquark pair, then I'm going to start adding gluons, maybe more quark-antiquark pairs. That's going to be my basis representation with the symmetries drilled in, similar to what I talked about for the non-relativistic problem. I'm going to have parity, I'm going to have angular momentum, I'm going to have charge conservation. All of that's going to be built into my basis. So any system I want to address, and once I have my Hamiltonian and my supercomputer, I should be able, in principle, to go out and start solving for its eigenfunctions and eigenvalues. So we've made a lot of progress in that recently. This started, the basic game actually traces its history back to some early work of Stan Brodsky and Chris Pauli, where they worked in a plane wave basis. But these days we find that plane wave bases are kind of hard on bound state problems. Bound state wave functions don't look like plane waves, bottom line. They have asymptotic tails which fall off exponentially, right? So we need a better basis. And the way to do that is to take your fields, in this case this could be a fermion or it could be a boson, and expand it in the language of quantized field theory as a superposition of respective creation and annihilation operators where these functions are not plane waves. That's the early days choice. These days we say they're rather general. They can be any convenient functions, similar to the choice of single particle basis I mentioned earlier. We chose harmonic oscillator earlier because of convenience. Well, we can choose harmonic oscillator again here if we want. Anyway, there's only general conditions that these functions have to satisfy, and let's take as our initial choice for solving this Lightfront quantized field theory problem, and we're going to apply it to mesons first as a 2D harmonic oscillator, two-dimensional harmonic oscillator. So our transverse direction will be a two-dimensional harmonic oscillator. And for reasons of symmetry, we'll take the longitudinal direction to be box normalized plane waves with suitable boundary conditions. So that's what's written on the bottom here in detail. Now, why pick such functions? Well, we don't know a priori the structure of our mesons and baryons and so forth. So we would like to have a basis that's flexible enough to have very complex structures emerge. If you take a look at the two-dimensional harmonic oscillator wave functions, you should know these from, say, normal modes of a drum head, right? That's just the way of describing these drum head modes. And they get very complicated even in the low-lying basis states of the 2D harmonic oscillator. So imagine that the solution to the problem is some superposition of all this complex physics. And that superposition is going to be driven by my chosen Hamiltonian. It's going to pick and choose the amplitudes of each of these configurations to make my ground state of my meson, my first excited state, my second excited state, and so on and so forth. So the 2D harmonic oscillator is a particularly convenient choice for the kinds of problems that we're dealing with. Now, I'm not going to do this in detail, but I'm going to just say that there are many steps to accomplish to carry out the calculation on a supercomputer. You have to set up your basis, you have to evaluate the matrix elements of your Hamiltonian within that basis. This defines a very large, sparse Hamiltonian matrix, which you then want to store on the supercomputer. Then you want to go through some process of getting its lowest eigenvalues and eigenvectors. That's roughly outlined here. There are many conditions. There's loops involved because of a process called renormalization. Quantum field theory, as you know, is a theory that generally encounters divergences, and we have to take care of those step by step. There are processes to do that within the Hamiltonian framework. And we've worked out the details. There's a sequence of papers that have appeared in the last few years that show these details. I'll skip some of the intermediate details and now show you some example results.
I just have a question.
Yeah.
So you showed the regular expansion. But that expansion, you can add a background field.
Yes.
Which is a constant operator 1. And then by adding that, it's equivalent to rearranging the box space so that you get to an infinite number of ordinary functions.
It depends.
Do you have any evidence for doing that?
Well, okay. Let's be careful. Depends on the background field that you're going to add. Yeah. Okay. If the background field is static, let's take away time dependence for the moment. We'll come back later to that. If it's a static field, it's just going to shift all my solutions because it's going to act equivalently on the center of mass of my system. And I've gone over rather quickly the details, and I didn't address the fact that what we are also very carefully do is set up our basis so that we factorize the problem into an internal problem and a center of mass problem. So that will affect the center of mass motion, but not the internal structure. I'd have to show you more of the details to probably convince you of that.
Sometimes you do that.
Sometimes we what?
Sometimes you put in a background.
We do, and that's coming. And I'll show you, we use it for a specific purpose. Yeah. Okay. So some test problems. You immediately would ask yourself, well, how do I know the theory is working, right? Well, we know a lot about quantum electrodynamics. So we can solve problems in QED that have been solved by perturbation theory. Just do it with this entire armada of non-perturbative results. And we can compare. And one of the famous test cases is the anomalous magnetic moment of the electron. And we get that to very high precision. And this is that process of extrapolating to the infinite matrix limit. You have two different schemes, both of which extrapolate independently to the infinite matrix limit. That's where this parameter, 1 over this parameter, goes to 0. And we get the calculated result of ordinary perturbation theory. So that's a test of the...
But you don't want to do that.
No, you don't want to do that except to convince... No. Thank you.
Yes.
We want to do better, but we have to prove to the skeptics that it doesn't screw up perturbation.
Why do you get the wrong result? Because first order perturbation theory is wrong.
Yeah, and there's a little difference of the order of alpha squared difference, or alpha to the fourth difference.
Which one's right?
Oh, we're right.
Suppose I don't believe in perturbation theory, and you have a better model.
Yeah.
Can you do that?
Yeah, sure. We're coming to the non-perturbative problems. Okay, so this is just to convince you we know how to do the extrapolations. And if you look really closely, this is positronium now, which is one step up. It's now electron-positron system. Perturbation theory does differ from positronium calculations according to ours by very small amounts of order, of the expected order of higher order perturbation theory. This is the order to which it's been calculated. That's what's shown on the figure there. Alpha to the fourth has been calculated, but not alpha to the sixth. Okay, so let me just jump to a few other applications. This is just to show you the kinds of things you can do with your wave functions, your Lightfront amplitudes. For those of you who are experts on generalized parton distribution functions, this is the generalized parton distribution function for positronium, just showing how different states of the system give very different distributions. Okay, don't pay attention to the details. I'll explain what's going on next. Okay, now we would like to jump to real physical systems such as charmonium, which is a heavy charm quark and a heavy anti-charm quark, and bottomonium, a heavy bottom quark and an anti-bottom quark dominantly. And treat that within QCD, Lightfront quantization, with the scheme that we've been talking about. The Hamiltonian is, now we don't have confinement solved yet in QCD, so we don't have a derived confining interaction. So we're going to adopt confinement from what's called Lightfront holography approach to QCD. So here's the Hamiltonian that we write down. It's kinetic energy for the charm quark, the anti-charm quark, or equivalently bottom, anti-bottom, confining interaction from Lightfront holography. Then there's another confining term that has to be introduced because this Lightfront holography, if you're an expert in this field, you know this, only gives confinement in the transverse directions. There's another direction that is not addressed with Lightfront holography, so we have to bring in confinement in that direction. And what we do is we match it to the transverse confinement so that this parameter kappa is the same for both longitudinal and transverse confinement. Then there's a one gluon exchange. QCD tells me I better put the gluon in. So that's not done in the holographic approach, so we've added that. Now what are the parameters that are to be fit? There's the confining parameter kappa, that's the strength of this confining field. It's quadratic, so it's like an R squared confinement. And the mass of the heavy quark, and that's it. We're going to fix alpha strong, that's here in the one gluon exchange, and solve the problem with two adjustable parameters. What do you get? Well, here's the charmonium spectroscopy as we know it today from the particle data group indicated in black. There's a whole group of states at each spin, parity, and charge symmetry, all the way across here. And although you can't see it, there's often a black line on each of these. There's a total of 8 states known experimentally below the breakup threshold into what is called the open charm systems. If you put too much excitation energy in the system, it falls apart into 2 subsystems, each of which carries one of those 2 charmed quarks. So basically, all 8 states that are seen experimentally are calculated in the theory, and that those 8 states are used to fix the charm quark mass and the confining strength. All the rest of the states, like these, are predictions of the theoretical calculation. Similar for the bottom quark system, except here I'm showing a lot more states. There are now, I think, 14 states known experimentally, and we get all 14. And then there's a few extra states that are predicted high up in the excitation spectra that are not known experimentally. I think this is one. And then over here, lots more states predicted, but are not known experimentally. These are the higher spin states, which would be difficult to see. Well, that one's known experimentally, but none of these. Difficult to see with existing experiments. So there are actual predictions now emerging from these calculations as well. Now we can go further. Now you have your light front amplitudes. What other observables can you look at? Well, initially we thought, let's look at the decay constants, the probability amplitude for decaying of these systems. So the quark and the antiquark can get together and annihilate, and that gives you a decay constant, the probability of that. And these decay constants have been measured for some of these states. That's indicated again by the experimental results with the blue dots and their error band. And then the red diamonds are our calculated results, and the uncertainties in our calculated results are also indicated. So I think there's a total of 5 known decay constants experimentally, 6 maybe, and then we've got a total of about 11, or with discounting the small ones, maybe 11 or 12 predictions. The agreement is not bad. We're a little high on the ones that are measured experimentally. We'd like to understand why. Maybe that's an indication we need to invoke more degrees of freedom in the QCD Hamiltonian. We're studying that right now. This is a plot from last week. So this is kind of the latest results. We can also calculate the radii of these systems. This is just to point out, these are very compact objects. Typically, the radius of these systems is about 0.2 femtometers, maybe 0.3 or so. But they're very compact systems, very strongly interacting compact systems. Now, I'd like to spend just a couple minutes talking about the next generation. After you've solved your bound state problems and you've got your spectroscopy and your transition rates between bound states, what else can you do? Well, these systems and this approach can be taken to the next level. You can actually make it into a time-dependent treatment of quantum mechanics. Now, where could that be useful? Time-dependent treatments might be imagined to be important when you have the combination of strong interactions and non-perturbative effects. So you want to solve the problem not at a probability level, not as a succession of Born approximations or something like that. You need to keep the coherence of the full quantum amplitude as you evolve the system under the influence of some very strong field. Think relativistic heavy ion collisions. Think high energy collisions in general. Think strong laser pulses acting on systems. All of these open up the door to the questions of whether non-perturbative effects need to be incorporated. Well, since we have the Hamiltonian already, we can now say, well, let's time evolve the system. Take the Hamiltonian as truly the generator of time evolution, but don't just take the static Hamiltonian we've been dealing with so far, add the external fields. So I come back to your question. Now we bring in the time-dependent strong external fields and see what that does to our systems. So that's the generalization. here's a picture of what one of these systems could be. Electron is at rest in the laboratory, so it's going to move up the vertical time axis initially. I'm going to bring a strong laser pulse which travels at the speed of light. Now watch what happens. This is just a cartoon of what's going to happen. So they're going to meet at the origin. Now the laser starts to act on the electron. The electron is initially going to be accelerated by that laser pulse. And at some point, if the pulse is strong enough, it can cause that electron, which is being accelerated, to radiate a photon, so-called Compton effect, the strong Compton scattering effect. And then you get final states where you have a photon freely propagating, electrons still being accelerated, possibly radiating a second time. And then it finally gets out of the laser pulse and then freely propagates after that. We have solved this problem at the amplitude level, treating it as a fully quantum mechanical problem. The electron is treated at the level of being a superposition of an electron and a photon, so radiation can occur. The laser is a strong external field laser treated classically, which is good enough for a very strong external field of high density. Okay, so just this is in a nutshell the calculational procedure. I won't dwell on that. We've solved this for the problem I've just showed you. Nowadays, we're turning our attention more towards heavy ion collisions. Consider that same electron we just talked about. What happens if I now, instead of hitting a laser on it, bring a relativistic heavy ion on it? Well, the Coulomb field, the vector potential generated by a relativistic heavy ion, is again a textbook problem, Jackson-level textbook problem. We can solve for that external field and treat that electron as a quantum mechanical object being acted on by that field. And that's what we're doing right now. The results are underway. And if I can, I just want to, for a moment, show you a little simulation here. This is a video clip, a simulation. And in this simulation, you're going to see the probability of where that electron is when it's hit by that, in this case, heavy ion, gold nucleus, both as you would see it if you did it in perturbation theory, that's the blue, and also with full time-dependent, non-perturbative action included. And so over time, what happens is, I don't know if you noticed the bouncing around, the perturbation theory immediately gives you some initial distribution of the final momentum of that electron after it's been accelerated. But the strong external field non-perturbatively populates much higher momentum states. At the same time, you saw the bouncing around going on. That's because quantum mechanically there can be feedback. You can not only excite something quantum mechanically, but you could also de-excite it. A full non-perturbative treatment keeps both of these on equal footing. That was the bouncing around. Okay, so that's one thing you can do. You can look at the transverse momentum distribution of your electron. Again, kind of an indicator of what's going to happen to that electron. The electron starts out, it's actually localized. I said it was at the origin, but it's actually a wave packet moving, it's stationary, moving very slowly in the transverse direction. And then it gets hit by the heavy ion so that it can be accelerated in the transverse direction. And then you can plot, again, a comparison between perturbation theory and the full time-dependent treatment. And here something quite surprising happened. The perturbation theory actually gave a stronger depletion at low momentum than the time-dependent treatment. The time-dependent treatment actually ends up dominating high momentum, but because of that feedback, it actually populated and depopulated some of those low momentum modes. I'll skip that. Okay, so now in the final closing minutes, and I want to leave time for discussion, I want to go back to the supercomputer story a little bit. I started out by saying I'm going to take a different approach here, and then I kind of slipped in some physics on you. Now I want to get back to the technical side, because I think for the students especially who are still making up their minds about their future careers, they might be very interested to know some of the things that are coming down the pipeline as far as developments are concerned. Now this is a busy chart, but I want to just tell you about the next few years. So Department of Energy is on this path now. They want to build an exascale computer. Probably 2021 or 2022 is the earliest date on which we can expect that to be a reality. In the meantime, the next 3-4 years, they're taking very big steps in that direction. And that's indicated by these 3 upgrades that are now underway. So in Berkeley, there's, this year they will deploy a 30 petaflop machine called Cori. At Oak Ridge National Lab, next year and the year after that, they're going to be busy deploying a 150 petaflop machine. Now remember, exascale is only about 6 times higher than that. So they're making the jump from their current Titan, which is 20 petaflops, 7-fold jump to 150 petaflops. Argonne National Lab, similar. They're number 5 in the world right now. They want to achieve more than 150 petaflops, but they'll take it somewhere in the 2018-2019 time frame. I had a wonderful lunch today with some of the grad students who were talking about postdoc opportunities that these 3 labs are advertising for physics majors to apply to. Stay in touch with that if you're interested in going this direction. Aside from the hardware, there's the issue of these are very complex machines. I didn't go into much details. They're highly parallel. They have very interesting interconnects, lots of topologies in the interconnect issue. How do you efficiently run any simulation you have in mind on such a complicated machine? This ends up being a research problem of its own value, and it leads to publications, often with applied mathematicians and computer scientists, trying to figure out how your problem can best fit on this very complex machine. It's a mapping problem. Complex physics on one side, complex hardware on the other. What's the efficient way to put them together so that you get full utilization of the machine and the full promise? Now, I won't spend any time on this, but as far as Hamiltonian eigenvalues are concerned, the tool of choice is called the Langshos algorithm. And it's been around for a long, long time. It's well recognized that it's computationally hard to put the Langshos algorithm to work on a parallel environment. Okay, so that's where we spend a lot of our research time. A lot of our time has produced very beneficial gains in how to do that. There's mapping issues, there's topology issues. If I take a Hamiltonian matrix of the type that we deal with in physics, it's a Hermitian matrix, usually written as a real matrix, and I only need to store the lower, say, diagonal part of it. And if I have lots of processors, I'll only put a piece on each processor. And now I have to figure out how, if a piece is on a given processor, how does it do the work necessary to get towards the eigenvalue and eigenvector of the full problem? Well, there's a mapping, and then there's interconnects and communication topologies that go about. And those are summarized here. I just want to point out this is a very complex problem. Multiple topologies are used for communications. If I'm sitting on a given processor, some of the time I'm talking to some processors, other parts of the calculation I'm talking to other processors, and vice versa, and yet another part of the calculation I'm talking to yet another subset of processors. So handling all this to flow smoothly, correctly, such that nothing gets messed up and everything stays in sync is a huge computational challenge. We figured it out. We've got papers published that show all of that. Now, on the software side, there is a code now, which will be published shortly, which does what's called many fermion dynamics. This is a general purpose code that will take any fermionic system that you care to try to solve. You input the matrix elements of the Hamiltonian, and it'll turn this huge crank on an arbitrarily complex computer to try to generate the eigenvalues and the eigenvectors for you. It'll do so with very efficient use of the local resources. So that's just kind of an advertisement. This is what we look at for scaling behavior. But I want to end now with, again, a kind of another advertisement for the grad students, maybe postdocs as well. So I often like to ask everybody, where do the supercomputers fit in your future? If you're just embarking upon a research career or a career in industry, are they going to come at you, or are you going to go at them, or where are they going to fit? Well, it turns out that it's not well known that there are a lot of companies making huge investments in supercomputers and are building up workforces in this area. You may not hear about the details because these companies don't like to tell you much about what they're doing. Think Google, Yahoo, Facebook, Amazon. Their information technology is part of their core capital now, and they're building this at a tremendous rate. If you look at the hardware they own and are purchasing, it's not on the top 500 list. They don't advertise it. They don't participate in those competitions. But I'm willing to bet you it exceeds what we're talking about that are available to the scientific community. So they need a good workforce that's capable of talking the language of supercomputers, solving problems that have not yet been solved on supercomputers, and your problem-solving skills could be the key. So, and I'm not just talking hypotheticals here. There are now case studies that you can go on the web and see companies that have used these supercomputers to advance their core competencies, their core businesses. One of the most celebrated cases is Goodyear Tire and Rubber. They shortened the product development cycle from 3 years to 1 year by simulations on high-performance computers. And they are one of the strongest supporters now of making high-performance computers part of the everyday technology in the workplace among US industries. This shows the growth in profits when they shortened their development cycle to get newer, better products through simulations. And on the web, you can go to Oak Ridge National Lab and you find page after page like this. This is a list of companies that have gone to DOE for competitive time. This is free to the companies. They have to compete for it, but they get awarded time on these supercomputers, these leadership class supercomputers. And these are your Fortune 500 companies. So again, not well known to the general public, but this is an emerging trend that could figure very prominently into your future research plans. If you're so inclined and want to go to work in industry, look at some of the problems that they're addressing. Lithium-ion battery simulations, cooling for cars, gasoline injectors, all sorts of combinations of physics, chemistry, and so forth are being put together in multi-scale physics, simulations, real-world problems, try to get an edge on the competition, a new product to market, more efficient, faster, and cheaper than the competition. As I said, there's several pages of these companies listed that you'd recognize in a moment. So with that, I want to thank you and welcome additional questions. Lots of questions, yeah.
Can I have you just move back to a slide so I can see it all?
Yeah, you want to read the company name? Go to the website
no,
because
I want to see the scaling slide that you
the scaling
and then
slide.
immediately pop through real quick.
Yeah, the scaling, the so-called strong scaling.
Yeah.
Okay. Question?
Yeah. So you run one of these simulations. How long does it take? And I mean, how much of that is actually trying to prepare the computer when you are actually using it, and how much is actually running on the computer?
That's a really good question. Of course, it depends on the application. In our typical calculations, we might take typically 50 to 75% of the whole computer and run it for 3 hours to get a set of solutions. We also, from time to time, take the whole computer. Some of our calculations are so demanding that we need to take the whole computer for a few hours. They have suitable queue structures that would run in the period of a couple or 3 days or so.
And then how long did it take for you to set it up? Is it months or is it?
Okay, it depends on what you want to allocate to the setup. The setup.
The last 30 years.
Yeah, 30 years. That's the answer here. No, I can make a run in as little as 15 minutes, set up and run, because we have to define the physics problem. That takes probably the most time. Figure out what's interesting to try to solve. Nowadays we have tools which we can bring together in very short time with scripts and make a run and get the results. The longest part of that might be just our analysis time after we get the results and then getting it into publication. Yeah.
Okay, now I've got a question. So first off, I may have this a bit mistaken. Jaguar uses one of the IBM really proprietary multi-core onboard systems with a management processor, if I remember correctly. So it has a really good scaling efficiency in general.
Okay, Jaguar was actually a Cray machine prior to Titan at Oak Ridge. But
Sorry, I mean the IBM technology in general, using management processors on local boards.
yes, okay, let's say the general point is well taken. Yeah.
Okay.
Yeah.
Sorry, I may have the.
Yeah, no, but
So this is, so this is kind of a best estimate scaling behavior.
We
I'm
were-
not saying, don't worry, I'm not going to
No,
be
no, no.
negative. I'm curious of your comment on something.
yeah,
So I agree, some incredibly powerful giant computers are being built. But one of the distinct trends in that is a massive increase in node count, shifts to more commodity designs like Knight's Landing, NVIDIA, so forth, that don't have a lot of these or these very clever extreme scale systems. What do you see as the future of this? How much of this is a computer science issue versus a physics issue versus maybe a fundamental algorithm rethink about which algorithms we go to as opposed to like Laxus and so forth?
so each time a new high-performance computer rolls out, you mentioned Knight's Landing, that's going to be Corey, we face major headaches because they change the technologies, the onboard technologies, the communication topologies, everything gets changed. They shrink the memory per core, and that forces us to rethink what we're doing in communications, all the rest. So actually, to answer your question, we have to go through a complete loop back all the way to the algorithm itself and do that several times with computer scientists, with applied mathematicians, trying to resolve bottleneck after bottleneck that the so-called disruptive technology deals us. And so the flip side of that question is, can we do anything about that for the future? And unfortunately, past performance is a guide of future performance here, and we've been very unsuccessful in getting the hardware manufacturers to listen to us about this kind of disruptive behavior that they're undergoing. That's because basic science is not a driver in the economics of these machines. It's what, maybe climate science or elements of the government that are big purchasers of these things want. So unfortunately, we're forced to deal with this at the basic science level, at the math level, at the computer science level. So we really have to struggle to keep up with those changes. Yes.
You attributed your bias from the experimental results to a lack of higher order terms. Was that because you're limited by your hardware time, or just what you've written?
No, it's actually the theoretical physics input in this case. We struggle with a lot of issues, some of which we just mentioned, and there's always a manpower issue, how you allocate. And this work is done by graduate students. I should have made a big point about this. Graduate students and postdocs are mostly doing this work. So they have to get a degree, and the degree is in physics, but they have to struggle with these other issues. So we've actually had to make sacrifices on the level of physics we can put in at the outset. We're coming back to that. We would like to put dynamical gluons in. We'd like to put more quark-antiquark pairs in. We're getting there. As I was mentioning to some of you privately, going to the baryons, going to tetraquark systems, pentaquark systems. This is our goal, maybe glue balls. But that is going to take, again, multiple efforts on the part of very talented people to upgrade all of this to those systems. So there's sacrifices we're making along the way. Yeah.
So, as someone who is interested in this as a potential career industry, what would be your number one suggestion of things to do to make yourself competitive as a PhD student in physics?
Build up your skills with parallel systems. If you have a PhD thesis that can be used as a test problem, by all means, try it out on parallel processors. try GPUs, get familiar with GPUs. These multi-core architectures, get familiar with Knight's Landing. NERSC is available on a competitive proposal basis for anybody to try to get time on it, and you can usually get 50,000 hours allocation as a startup grant to start your calculations up and get your codes running and try it out. So basically, don't be afraid of them. You have to dive in. It's like learning anything else. You'll build up your knowledge base over time, and it'll look really great on your resume if you say you have experience in parallel computing. So,
More questions? Well, let's thank Professor Berry.